All right. So we're going to talk today, we're going to continue talking about this discretization idea. And one of the things I want to emphasize again today is the role of CFL and why this is dropped in conversation all the time. I don't know if you've had conversations about numerical analysis, people setting up schemes and codes and stuff. But usually someone will say something like, oh yeah, what's a CFL? They'll say CFL in the conversation somehow. And it becomes important for the following reasons. We've already seen how it plays a role in terms of making a scheme stable. But I want to highlight a few other things about the CFL and how important it is in terms of starting to think about stability of schemes. So let's go back to our prototype equation, one-way wave. And what we've been doing with this is saying, okay, so I want to discretize this, and what we already know from the discretization process is that if I discretize this using forward Euler, it's always unstable. But if I discretize using leapfrog, 2, for instance, it's stable for lambda less than 1. So in particular, let me write down the scheme that we had if we do this leapfrog scheme. Here it is. Point in future is what it was one time ago plus some stuff. This is the derivative term. Your two neighbors making a contribution to your future. Okay? All right. So what we learned from this was that if lambda less than or equal to 1, this scheme was stable. Okay? And by the way, lambda itself is C delta t over delta x. All right? Yeah. Okay. Okay. There we go. That's the condition. So we derived this. We said, boom, there it is. In fact, what we did to derive this condition, right, is we started talking about this von Neumann analysis. And the whole point of the von Neumann analysis is to say, tell you what, let's go ahead and throw in frequency components, content into this thing, and just see what happens if I have a bunch of Fourier modes in there. Not a bunch, just individual Fourier modes, but I just pick out some generic frequency, and all I care about is, do the coefficients of any of those Fourier modes grow to infinity? And if they do, you're unstable. Okay? So the idea then was, for the von Neumann, was to say, let's do the following. If we think about that as our nth time, nth position, then what you say is, I will let this thing look like the following. Here. Okay, so let's again recap what this really is trying to do. It is a limited class of solutions, if you want to think of it. It's a limited class of function that you're going to look at in terms of the stability analysis. Remember that this von Neumann analysis only tells you something necessary, not sufficient. Okay? But if this blows up, you know things are not going to work. So that's what actually what you're after is at least here's one measure of saying, if these Fourier modes blow up, I'm done. And how do you know if the Fourier modes blow up? You ask what's happening to G as you raise it to the nth power. If this absolute value of G is bigger than 1, then if you keep taking a number, raising it to infinity powers, it's going to go to infinity. Okay, that's all you're asking about this. And it's limited, but it does tell you how a single Fourier mode might grow. Okay? And remember, this is sort of generic, so you can pick these to be anything. All right. So that's the idea behind the von Neumann analysis, to get us some information out. Now, we did all of this analysis for the one-way wave equation. Right? So last time in class it was very exciting. As we worked our way through this von Neumann analysis for the one-way wave equation with the forward Euler, the backward Euler, the leapfrog 2, McCormick scheme, right? We hit all these ones and saw that It doesn't look that much different in terms of the iteration, but a huge difference in terms of stability. Okay? So that's how we did for the iteration. Now let's actually start thinking about, well, let's apply the same idea now to actually a slightly different equation. And, oh, by the way, when you plug this into the leapfrog, here's what you got. If you remember, something like this for the relation of g. And then if you can basically multiply by g, find the roots of this thing, look at this thing, and you ask, when is g bigger than 1? Or the absolute value b bigger than 1. And so you find that absolute value of g is less than or equal to 1 for lambda less than or equal to 1. And that's your stability criteria. I think that's what we actually didn't work that all out, but I just told you what the result was. Okay. Now let's consider a different equation. Heat equation. Just added one more space derivative. Doesn't look like that much of a different of a, we went from here to here. Pretty simple change. Totally different behavior, by the way, these two equations. This equation models wave phenomena, waves propagating around. This here models diffusive behavior. Solutions eventually go to 0. So this is sort of a dissipation process, whereas that's waves. There's no dissipation in this. So it makes a big difference, that one derivative. And it's also going to make a big difference for us here today as well. Okay. All right. So let's go ahead and start to discretize this thing. So the first thing we want to do is discretize spatially. Now here's going to be the big deal. Now remember, u of x was just use your neighbors, and it's a slope formula. Point in front minus point behind. Well, we're going to use the same kind of formulas here for uxx, but now slightly different. It's u point in front minus twice the current point, point behind, all over delta x squared. Okay? So if you start thinking about that, then you have this equation upon discretizing spatially. One big thing to notice right away, and this is part of what I want to pound into your head today. Okay? Do you feel it? Yeah. Ow. Just let it through. There's a delta x squared on the bottom now, not delta x. And you say, oh, well, big deal. It's the hugest deal in your life, like the next 50 minutes. 40, actually. Okay, that's all you have to think about. What's the biggest deal in my life right now? And your answer should be, oh, that delta x squared sitting on the bottom. Of course, that's the biggest thing I ever saw in my life. You make a big deal of it, okay? Today. This is why CFL is important, because there's a delta x squared sitting there. And now what we're going to do is we're going to discretize in time. Okay? All right. Now, how do we discretize in time? You know what? Leapfrog seemed to work pretty well for us before. In fact, Euler, for the one-way wave equation here, was always unstable, and Leapfrog worked. So let's just try to do Leapfrog here, since it seemed to have worked. Okay? So I'm going to put that in. So Leapfrog would say, take a point in the future minus a point in the past all over 2 delta t. Slope formula. And the idea behind the Leapfrog is you don't use the current point and future point, you use the current point in one past. And that's equal to this over here, and let's evaluate this side at the current time. Okay? Now I'm going to multiply by 2 delta t, move that over to the other side, and I'm going to have my scheme. These are at n. Point in the future is what it was one time ago. Okay? All right, plus 2 lambda, and I'll tell you what lambda is in a minute. Un plus 1 m minus 2 un m plus un minus 1 M. There you go. There's your leapfrog scheme for the derivative. And now I have a lambda, and this lambda is not delta t over delta x. This lambda is delta t over delta x squared. And you remember, the biggest issue in your life right now is that delta x squared sitting underneath there. Why does it matter? Because you asked the following question. Hey, you know what? I don't like my accuracy. What are you supposed to keep tabs of is your accuracy in your code. So you say, I don't like my accuracy. I want to double my accuracy. So that means you have to double the number of points. Cut your delta x in half. Ooh, cut it in half. You're going to square that. Factor of 4 on the bottom, which means to keep the same CFL number, you've got to take your delta t down by a factor of 4. How much more time is it going to cost you to double your accuracy? 4 times 4. You see how you're going to have problems? Hopefully, yeah? So you did you did twice the amount of work here, 4 times 8. Sorry. I can't do math. This is all a sham. I'm a suit guy. Come on. Just tell other people, you do the math. I'm going to make money. Okay, all right. Factor of 8, sorry. Yes, so you do twice as much work here, twice the number of ODEs, and you have 4 times smaller steps. So that is how much slower your code is going to run. Okay, now you may think, big deal, I hit return, and then I waited 10 seconds instead of 2. All right, I have a code. I want to scale this up. I'm solving a Boeing thing. It's going to take a supercomputer. I'm working on this thing. It takes 3 days. Okay, you need more accuracy. Ooh. Okay? Do you see how important this is? And all of it is driven by the fact that you have a second derivative. This delta x squared on the bottom is due to adding an extra derivative there. So the CFL, even if you can't compute the von Neumann analysis, this is a very simple problem. We can do the von Neumann analysis completely out. But what you know is if you have a code that works, and perhaps it's a nonlinear PDE and you're solving, and you know that the CFL number has to scale like this, you want to double your accuracy, be prepared to pay 8 times the amount of work to do the code. Okay? That is what CFL ultimately measures. Ratio of time to space steps and how those have to scale together with each other. Or you say, okay, fine, big deal. I can wait 8 seconds instead of 2 or 1 or whatever it costs me. Okay, because in our codes that's what's going to be the case for right now. At least our demo codes we're going to do in class. But let's go back now and address this issue. We'll come back to that CFL issue in a moment. But right now we're going to come back to here and just ask, okay, I lose leapfrog now for a heat equation, which worked with the wave equation. And so I want to see how well this works in this case here, is to do a von Neumann analysis.